Is everyone ready? Let's get ready for chemistry!
Now let's talk about formal charges. A formal charge is kind of like a charge that an atom feels like it's experiencing in a Lewis dot structure. Sometimes it's a real charge and sometimes it's just what it feels like. To calculate the formal charge, we take the number of valence electrons for that atom and we subtract from that the number of non-bonding electrons on that atom plus the number of bonding electrons divided by 2. So an atom feels like it owns each of its non-bonding electrons plus half of the electrons involved in bonding. And it should have its number of valence electrons. This looks really complicated. It's actually not complicated at all. Let's look at our nitrate ion and let's calculate formal charges for all of the atoms in this nitrate ion. First off, let's calculate the formal charge for that nitrogen there. The nitrogen has 5 valence electrons and it feels like it owns 1, 2, 3, 4. It feels like it owns 4 electrons, so its formal charge would be +1. So this nitrogen is experiencing a +1 formal charge. Now let's look at the formal charge for this oxygen atom here. So this oxygen atom, oxygen has 6 valence electrons, and this oxygen atom feels like it owns 1, 2, 3, 4, 5, 6 electrons. So it owns half of the bonding electrons, 1, 2, and then all of the non-bonding electrons, 3, 4, 5, 6. So this oxygen has a formal charge of 0. Now let's look at the formal charge for this oxygen. Oxygen has 6 valence electrons, and this particular oxygen owns 1, 2, 3, 4, 5, 6, 7. So this oxygen owns 7 valence electrons, so he's got a formal charge of -1. And then this oxygen over here is experiencing the same thing. 6 minus 1, 2, 3, 4, 5, 6, 7. So he's also got a formal charge of -1. And if you look at the formal charges on this structure here, the -1 plus the -1 plus the +1 plus the 0, this adds up to -1, which is the overall charge of the ion. So your formal charges should add up to be the overall charge of the compound or the ion. Let's look at the formal charges involved in our silicon tetrafluoride. First, let's look at the formal charges involved in this silicon atom here. Silicon has 4 valence electrons, and it feels like it owns 4 electrons because it's got 8 bonded pairs, and half the bonded pairs is 4. So this formal charge is 0. These 4 fluorines are all experiencing the same thing. These 4 fluorines all have a single bond with 3 lone pairs of electrons on them. So if we calculate the formal charge for one fluorine, it'll be the same for all 4 others. Fluorine has 7 valence electrons. This fluorine feels like it owns 1, 2, 3, 4, 5, 6, 7 for a formal charge of 0. So 0, 0, 0, 0. Let's calculate the formal charge for the xenon. Xenon has 8 valence electrons, and this particular xenon feels like it owns 1, 2, 3, 4, 5, 6, 7, 8. This one feels like it owns 8 valence electrons for a total of 0. So the formal charge on that xenon is 0. This one's going to get interesting. So let's calculate the formal charges for the carbon. This carbon here has 4 valence electrons, And we're going to subtract from that 1, 2, 3, 4. So 4 minus 4, this carbon has zero formal charge. This carbon down here, same thing, 4 valence electrons minus 1, 2, 3, 4 gives us a formal charge of 0. And then of course this carbon is the same thing with a triple bond on one side and a single bond on the other. Now let's calculate the formal charge of the sulfur. This particular sulfur has a double bond and 2 lone pairs. And then the sulfur on the other side is experiencing exactly the same thing. So sulfur has 6 valence electrons, and we're going to subtract from that 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So this sulfur has a formal charge of 0, and that sulfur has a formal charge of 0. This sulfur here is a single bond with 3 lone pairs, and this sulfur here is a single bond with 3 lone pairs. So this sulfur here is experiencing, there's 6 valence electrons in sulfur, and it's got 1, 2, 3, 4, 5, 6, 7 around it. It's actually got a full octet, but what's its formal charge? Its formal charge here is negative 1, and then this one's got a formal charge of negative 1. Starting to run out of colors here. This sulfur and this sulfur are both experiencing a triple bond with a lone pair. So sulfur has 6 valence electrons, and we're going to subtract from that 1, 2, 3, 4, 5. So this sulfur has a formal charge of plus 1, and this sulfur has a formal charge of plus 1. Now in this molecule here, negative 1 plus 1 plus 0 equals 0, which is what it should equal because it's got to come out to be electrically neutral. So these are the formal charges for the 3 resonance structures here. Let's look at the formal charge for this carbon. Carbon has 4 valence electrons, and we're going to subtract from that 1, 2, 3, 4. So this carbon has a formal charge of 0. These 3 hydrogens are all experiencing the same thing. 1 single bond. Hydrogen has 1 valence electron, and this one feels like it owns 1. So 1 minus 1 is 0, so these hydrogens all have a 0 for a formal charge. This chlorine here has 7 valence electrons, and it feels like it owns 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is 0, so this chlorine feels like it has a formal charge of 0. So who cares about formal charges? If the compound contains many 0 formal charges of 0, then that compound is going to be more stable. So the more zeros you find in a structure, the more stable that structure is. Structures can have formal charges of negative 1 or plus 1. Those are okay, but molecules tend to want the negative formal charges on the more electronegative elements, if you have a choice, and the positive formal charges on the less electronegative elements, if you have a choice. That tends to be more stable. Lastly, if you have a formal charge that's greater than plus 1 or smaller than minus 1, like a minus 2 or a minus 3 or a plus 2, that tends to be incredibly unstable. Not that it can't be possible, it just tends to not be as stable. So what do formal charges do for you? One of the things they do is to help you decide whether or not a molecule is stable. I would expect this molecule to be fairly stable based on its formal charges. I've got a bunch of zeros, so stable molecule. Here, I can rank the resonance structures based on which resonance structure is the most stable. So in this top one has 3 zeros. All of them are 0 formal charges. I would expect that particular structure to be very stable. This second one here has a plus 1 and a minus 1 that I guess you could say they aren't really necessary. So I would expect that to be less stable than the top one. So this one and this one are less stable because they have less 0 formal charges. And this one is the stable resonance structure because it has more 0 formal charges. What does that mean? That means when you've got resonance structures, it's going to spend more of its time as this one and less of its time as the other two. Phosphate is interesting. We would not have thought to draw resonance structures for phosphate. The reason being, the phosphorus already has an octet. When you look up, for example, if you were to look up adenosine triphosphate, ATP, and you were to see the structure for that, what you would see is something that looks like this. Most phosphate, when you find it, has a double bond in it. Why in the world would phosphate have a double bond? It already had an octet. The answer is, these rules are not rules. These rules are guidelines. So let's draw all the possible resonance structures for phosphate. There are quite a lot of them when you expand the octet and create a double bond. Having more resonance structures, more possible resonance structures, also contributes to the stability of the molecule. So since we can draw 5 resonance structures, we predict that this phosphate ion would be fairly stable. Now let's draw formal charges. Let's calculate formal charges for this. This phosphorus feels like it owns 5 minus 4, so it would have a formal charge of +1. These 4 oxygens all have 6 minus 7, so they all experiencing a formal charge of -1. There are no zeros in this structure. I would not expect this structure to be fairly stable. However, when we start looking at the formal charges here, this oxygen has 6 minus 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So this oxygen has a formal charge of 0. This phosphorus is 5 minus 1, 2, 3, 4, 5. So this phosphorus has a formal charge of 0. And then as we saw before, these single bonded oxygens all have formal charges of -1. That would mean that this resonance structure is actually more stable than this resonance structure because this one has more zeros. It's got 2 zeros as opposed to no zeros, which is why when you find phosphate, it's usually drawn with a double bond. Even though that expands the octet, even though we decided in the rules that that wasn't necessary, it's going to do that anyway because it has more zero formal charges. Now, as long as we're going crazy, let's just go whole hog. Couldn't you also expand the octet twice and have 2 double bonds? Yes, that's possible. Now let's look at formal charges here. This phosphorus has 5 minus 1, 2, 3, 4, 5, 6 for a total of -1. And then our single bonded oxygens were all -1. And then our double bonded oxygens were 0. So this resonance structure would not be as stable because the negative formal charge is not on the more electronegative element. This is still the most stable resonance structure because it has the most number of zeros and the negatives are on the more electronegative atom. So when you see phosphate, you would see it with a single bond. These are all possibilities. But the most stable one is going to be these in here. because of the way their formal charges work out.
Is everyone ready? Let's get ready for chemistry! Ah! Yeah, 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 yeah.